Hello, my name is Stephen Bowers. I'm an assistant professor at the University of Virginia, and I'm going to talk to you guys today about the adaptable receivers we've been making for self-powered wireless sensor nodes. The title of the talk is called Asleep Yet Aware. And basically what we're talking about is wireless sensor nodes that are so low in power that they can be powered by the environment around them, and yet are still small enough to be able to fit into our everyday lives without changing the form of the devices that they're being integrated into. In order to do that, we're going to keep them asleep for most of the time. But at the same point, we can't let them stay asleep for too long. And so even while in their sleep state, these nodes need to be aware. And that's where the wireless adaptable receiver is going to come into play. So first, let's talk a little bit about applications of these very, very low power, what we'll call near zero power sensors. At some point, if we can get the sensors low enough power, we can start to put them kind of everywhere around our daily lives. One example of this that's probably most common today is in smart homes, right? Right now, you might be able to go out and buy a thermostat, various types of light bulbs that can all connect back to the internet and make your home smarter, utilize less energy, and because of that, have a lower carbon footprint and environmental impact. There's a lot of other places that we could start to add sensors to. For example, in emergency response, imagine if when a fire truck got to a burning building, instead of having to go in and use external infrared sensors to try to determine where people were inside, imagine if the sensors inside the building could tell the firefighters as they drove up where the potential people were that were trapped inside the building. Another really big emerging application for adding lots and lots of very low power sensors is actually in smart agriculture. Turns out that we lose a whole ton of our crops, the efficiency of the crops each year, because we kind of do blanket agriculture, meaning we put the same seeds across a very large field. They get reasonably similar levels of water. But if we had sensors in the field that could sense how much sunlight given areas of the field got, and the pH levels and the moisture levels, we could customize our agricultural responses and improve the yields tremendously. Another big one that's currently out there is in health and fitness. Turns out that people can get motivated by fitness tracking, whether it's on their body or in the environment around them, promoting healthier lifestyles. But on top of that, the more we can add sensors of biological signals onto people, we can get readings of their health status, not just when they're at the doctor's office or at a hospital, but rather throughout their everyday lives. And that can provide very valuable information and early detection of a variety of health issues. Another important application comes in the form of industrial monitoring and inventory tracking, where you might want to be able to determine the status of a variety of your industrial equipment, perhaps on where your inventory is and if it's been handled in the correct manner from both temperature, perhaps, or movement. All of these applications inherently rely on the vision that we're going to have a whole lot more connected sensors in the future than we do today. But even if we start to look at how many sensors we have today, we'll quickly realize that the number of connected devices outnumber people by a factor of 2 or 3 to 1. And this exponential curve in the number of IoT devices compared to the number of people on the planet mean that very likely soon we could imagine networks, global networks that would have about 1 trillion different nodes in them. Now, this is a real big problem for nodes that are powered by batteries, because if you're going to try to change 1 trillion batteries, even if these devices have years-long battery length, you're going to still be employing 8 million people full-time just to change the batteries or charge the batteries. It's just not sustainable. We need to find ways that we can have these things sustain themselves through energy harvesting through environment. One of the issues with that is that they have to be very, very low power. And so in order to figure out how to make them low power, let's take a look at the anatomy of one of these types of sensor nodes. Turns out that as you make more and more sensor nodes, all working collaboratively in our environment, the amount of time each individual one is required to be on reduces significantly. While we might have a main controller, microcontroller to do computation, memory, power management unit, data transceivers, and different sensing units in a sensor node, most of these things can be turned into a sleep mode for most of the time in an event-driven environment where you're using the sensor very infrequently. However, in order to still allow that sensor to be used when it needs to be used on demand, it has to maintain this awareness. And that awareness is provided through the use of a wake-up receiver. Essentially, the wake-up receiver is one of the only always-on components of our smart sensor node that is always listening to the environment for an RF signal that's telling it to wake up. So when you have a need to use that sensor, you can wake it up from the network. How we do this is really determined by how much energy we have to provide. You might think that a sensor network uses most of its power in the active mode, but as the activity factor, which is measured in essentially events per hour, decreases down to kind of tens of events per hour, 1 event per hour or less, we can quickly see that the amount of current that is utilized in the sleep or dormant state will dominate over the active power. And if we want to be able to get our nodes really, really small, let's say millimeter sized and below, and we want to be able to operate off of a variety of energy harvesting modalities. So let's take one that's reasonably low, indoor solar, as a metric of energy per square centimeter. We're finding that we really need to keep the sleep power of these nodes down below, let's say, 100 nanoamps or a couple hundred nanoamps and below. And that puts a hard limit on the amount of power we can spend on the wake-up receiver, because if our wake-up receiver is always on, 100% of that power is going to be going into that sleep current, sleep power. So this is the challenge that we've been working on over the last several years. And one thing we can look at are some of the metrics that we care a lot. I've talked already a bunch about DC power consumption, the fact that we need to keep it at maybe several hundred nanoamps or below. The other big metric that we care a lot about is sensitivity. Essentially, what's the smallest signal that I can detect at these power levels? And we measure that in dBm, the amount of RF power that's required. And we can kind of separate it into two different modalities for wireless transmission. Things at around minus 75 dBm or above are more short range transmissions. Think about like Bluetooth or maybe Wi-Fi. If we can improve the sensitivity even farther into the minus 80, minus 90, even past minus 100 dBm, we can start to think about using these things in a much longer range in kind of kilometers or tens of kilometers. Think more about like cell phone distances. And so our goal throughout these projects was to both simultaneously reduce the DC power consumption and increase the sensitivity. More negative sensitivity is better. And as you looked at where the state of the art was in 2016, we found there was this kind of limit, right? You could spend a lot of power and get very sensitive receivers, or if you wanted to make very low power receivers, you were still operating at very, not very sensitive numbers. And so the project was essentially trying to push us first down into this range of low power, and then eventually into very high sensitivity while maintaining that low power. So how do we do that? We made 3 critical observations. The first is that if we want to get in kind of the tens or even hundreds of nanowatt power levels, we really need to use a simple receiver architecture. Can't use a lot of these very complex architectures that have a variety of components that just utilize a lot of power. But we can actually have quite a bit of digital control, especially if that control doesn't need to change often. We can make algorithms that activate or modify our receivers in real time to have them operate optimally for their given environment. The second key observation is that we're only really transmitting kind of maybe tens of bits of transmission in order to wake a node up. If you think about it, it's actually really only one bit, right? Like wake up, right? Or not, right? That's one bit of information. The reason we send more than just that one bit is we want to be able to say, you wake up, right? So we want to specify a specific node and not wake up all the nodes if we want to yell wake up, right? So anyway, we can do that with kind of tens of bits of transmission. This is a pretty low amount of data, and so if we lower the data rate, we often can integrate our signals for longer and get better sensitivity for the same amount of power. The third critical observation, and this is what really allowed us to go from just low power to something that's very low power and high sensitivity, is that while the wake-up receivers need to appear to be always on, we can actually implement them in a way where the power consumption is not constant. It allows us to use higher power blocks, but use them infrequently. And thus we can achieve the higher sensitivity at lower average power. But we do it in a way where from the outside, it looks like this wake-up receiver is always on. So we can look a little bit at the types of receivers we've been implementing. Well, the first one at the top is kind of the default, most traditional receiver that is used in most radios today. It's called a heterodyne receiver. And what it does is it takes an input signal and it amplifies it. It then has a high frequency source. This is a very precise source that's utilizes a lot of power. And that converts this RF signal down to a much lower frequency where you can digitize it and maybe do some baseband processing. There's a reason we use it a lot. It's very sensitive. It works really well. But there's no way you're going to get this down to the kind of hundreds of or tens of nanoamps of power consumption simply because the frequency synthesis, generating this frequency source, is just going to take more power than that. So we try to go to much simpler architectures. The first one we explored was probably the most simple architecture you can think of. It's called the detector first architecture. You basically have some filtering, perhaps, maybe some impedance matching at the front, and immediately just use some sort of envelope detector, meaning you're detecting how much power is in the signal. You have a little bit of amplification you can do at the low frequency there, and then you do some digital processing. We utilize this to take the DC power down to tens of nanowatts, but we found after the first couple generations that we hit a wall where we couldn't get past about minus 80 dBm sensitivity in a standard CMOS process. That led us to think about how we could overcome that limit. And as I said, we did that through the observation that we can use higher power blocks as long as we use them infrequently. And so we added a RF amplifier that's shown here. It's before the envelope detector. And what that does is it allows us to break this kind of noise and power trade-off. And we do it by duty cycling it. That's kind of weird because we said, oh, this is our always on component. But because our bit rate is so slow, we can actually turn it on, take a measurement really quick, and then turn it off again. Call this within bit duty cycling. And it does enable us to get better than minus 100 dBm sensitivity, which is this kind of cell phone long range sensitivity, while maintaining tens of nanowatts of power consumption. If we look at that same plot as to where we are today, you can see these first two generations that we did in our lab were that envelope detector first architecture that I mentioned. And the newest ones that we've been exploring over the last year or so are what we call this samplifier, meaning we amplify only right when we sample it. So we call it a samplifier. And we were able, year over year, to make a 26 dB improvement in sensitivity, getting us from the kind of Wi-Fi sensitivity ranges all the way into kind of cell phone range. And if you look at it compared to what was happening before this effort started in 2016, it's an incredible improvement of 62 dB in sensitivity. And in addition to that, a reduction in 3x in power. So this is a really exciting result that we think is going to really enable the sensor nodes of the future. But what is next? While it can enable this, we've got a lot more work to do and things that we're currently working on in the lab. If we want to have the whole node be on the order of millimeters or smaller, it's not just the communications or even the digital together, but it's a co-design of the entire node. We're going to implement antennas that interact with the photovoltaic energy harvesting surfaces in a way where both can utilize the outer surface area without damaging the performance of the other. We have to have digital computation on the same chip as our communications ICs that all run off of very low power and are able to take the data that you've sensed and transmit it back to the internet. So that's what we're looking at next. I get the pleasure of explaining all this stuff, but I didn't do much of the research itself. The grad students did all of it, and so all the acknowledgments go to them. I worked in collaboration with 2 other professors on this project, Ben Calhoun, Scott Barker, sorry, 3 other professors, Ben Calhoun, Scott Barker, and Songbin Gong at University of Illinois. The funding support for this was from DARPA and NSF. Here's a list of some of the references of the publications that came out if you want to look more into this work and learn more about it. And if you want to get in touch with me, you can find my email address on this slide. Thank you so much.